Okay, let's get started today. I want to tell you a little bit about an aspect of my research and the things I study. I'm Ed Kinney. I came to the university many years ago. I'm afraid to mention how many years ago. And all my career here, I've worked on trying to understand the structure of the proton. And I want to tell you a little bit about it today and hopefully make it clear just why I find it as fascinating as I do. So I started off with a title about the strongest glue. Well, here's the oldest glue. This is rawhide glue. This is like 200,000 years old that people learned how to make some kind of glue out of the hide of animals. In our more modern times, we have things like super glue, or I grew up with Elmer's glue, all of these kinds of standard glues. And I don't know if you ever saw that picture before, but it sold a lot of glue having that. And of course, we like glue, we like it to be strong when we stick things together. So what is the strongest glue that I claim? Well, if you look at the regular chemical glues, it typically will hold, an epoxy glue will hold around 6,500 pounds per square inch, which is pretty darn good if you think about it. That's like holding up a car with something this big. So those are not the epoxies you buy down at the hardware store, but they are industrially made. It's quite amazing. But my question is more, what's holding the glue together? What about the atoms and the molecules in the glue? How can they be held together? Why don't they rip apart? And what actually is holding the components of the atoms together? And how far down do I have to go before I really don't have to hold it together anymore? Before it is a thing which is just itself, which we tend to call a fundamental particle because it doesn't have anything else inside it that you have to hold together. So that just brings me then to this sort of question. What is matter? We think of matter as fundamental particles, these ones that can't be split up anymore, held together by some kind of forces into the things that we see around us. So for instance, let's start down the chain. Atoms are not fundamental. They're made up of things that can be split up. They've got a very tiny, heavy nucleus, and it's surrounded by some electrons. It turns out the electrons are fundamental. We've never been able to split an electron into anything smaller. And in fact, we only have an upper limit on its size, that it's about 10 to the minus 18 meter. It could be smaller, but we don't know. We've never found any evidence that it actually is made up of something. It's very light. If you do it in kilograms, which isn't the great unit for this, it's 10 to the minus 31 kilograms, quite small. And it has an electric charge that's, again, in a unit which isn't very useful, 1.6 times 10 to the 19. That's just a very, very, very small amount of a coulomb, which is a big, big charge unit. So that actually is a little bit special. I'll come back to that, is that fundamental value of E seems to be special in the universe for reasons we don't really know. All right, let's go inside that atom. We're going down the atomic nucleus. It's also not fundamental. We can break it apart. It's made up of protons and neutrons, which are these kind of heavy particles. If you look at a hydrogen atom, the nucleus of the hydrogen atom is just a proton. The neutrons are neutral, as the protons have a charge, but they're about the same mass. They're very similar particles. But they're not fundamental. They have a size, and we've learned that we can break them down yet again into other particles. And those other particles, we think, are the quarks. And the quarks, indeed, we have not found that they can be broken into anything smaller. We think that is the fundamental piece that goes into making up protons and neutrons. All right, so they seem fundamental, and let's go through the forces before we attack the quarks a bit. So we all see the galaxies and stars and planets around us. There you see gravity at the fore. Gravity is holding all of this together, and all the amazing things you see in the Webb satellite pictures are testaments to what gravity can do. Atoms and molecules are mostly held together by electromagnetic forces. Electric forces mostly, but there are some magnetic ones in there as well. And these are ones which are stronger at a short scale, but by the time you get out to long distances, they shield themselves so that you don't actually see the effect of them that much. Although in intergalactic space, they can be pretty sizable. If you go inside the proton and neutron, we have the quarks, and those are held together by something called color forces. And I will spend some time trying to describe to you how that actually works with this thing called a color force. But the real point is, with just those three forces and the quarks and the electron, we basically can describe matter from the galaxy-sized objects down to these very, very, very tiny objects. And so that's sort of a goal, is to have a unified understanding of all these different levels of nature. So let's just go through the quarks. Not everybody's been indoctrinated with quark lore. They have rather whimsical names. So when they were first invented in the 60s, one of the people who made them up was quite proud of using sort of weird names, quirky names. So quark actually comes from James Joyce's Finnegan's Wake book. And you'll see other little whimsical things. So there's an up quark and a down quark. And these are the first particles we find that have a fraction of this fundamental charge E. Amazingly, when they make up a proton or a neutron, it always evens out so that it is E. And that's sort of a mystery of why that is necessary. And they have masses, which again are quite small. But if you remember the electron, that these are actually bigger. They're more massive than the electron. The proton and the neutron are mostly up and down, but it turns out there's other quarks, and some of them even exist inside the proton and neutron. The next heaviest is the strange quark, again, rather whimsical name. It is a third E, just like the down quark, but now it's significantly heavier, whereas the down quark was just 8 times 10 to the minus 30. This is 240 times 10 to the minus 30, so it's quite a bit heavier, but we're not done yet. We have the charm quark, which is more like the up quark, but it's even a factor of 10 heavier. And then finally, we get to the bottom quark, and it's even 4 times heavier than that. So somehow nature has made up these quarks, and they have these increasing mass scales, which we don't understand where they come from or why they're needed. But we don't find any quarks after that. We haven't found any, at least. So that's sort of where that story ends. Now, oh, I forgot the top quark, sorry, even bigger. We have to have 6, right? 1, 2, 3, 4, 5, 6. So then there's the other fundamental particles on the electron side. So there's a heavy electron called the muon, which when it was discovered in the, I believe, the 30s, one of the people said, well, who ordered that? Why do we need this particle? And I'm not sure anybody knows why we need it. And yet there's another heavy charged electron called the tau, which you can see is quite a bit heavier. But it's been discovered and produced in the lab. Then we have their cousins, the super light neutrinos. Now instead of having hundreds or thousands times 10 to the minus 30, I'm at 0.004, and that's just an upper limit. We don't really know what the masses are. We have some idea of some mass differences, amazingly, but we actually don't know what their actual masses are. The muon neutrino is expected to be a little heavier, although that's really just an upper limit. And the same, there's a tau neutrino. So we have these sort of families that come in pairs, that then there's 3 generations of these particles that make up our standard set of particles. This on the electron side, just so you get a little bit of jargon, these are called leptons, right? So is that all? Well, people still look for other neutrinos. There may be more out there. And then I think everybody has probably heard that there's active searches to try to find dark matter particles. Dark matter is something you infer from seeing how galaxies are forming and moving, and you infer that it is there, but no one has ever actually discovered a dark matter particle. So there's still lots of new things to be looking for out there. All right, there's lots of mysteries about these. Why do these extra heavy particles exist? We don't know. Why are there only 3 generations? Why is there just a cascade of them up 4, 5, 6, 7, 8? We don't know. Why are their masses so different, right? If they'd all been sort of close, or maybe a factor of 2 or something, but they're very different. And they're sort of oddly spaced, too. They don't follow a pattern that's easy to discern that would make you think, oh, it's some kind of mass generation thing. And then, of course, a lot of people are trying to find out just what the masses of the neutrinos are. And then, for me, one of the special ones is, what is so special about E? Why do they always have to add up to E? Even when I take subparticles, which are less than E, I can only create a stable state that has a charge plus or minus this basic charge constant. All right, so let's go back to forces. I want to review a little bit about, because I'm going to contrast with it, electromagnetic type of forces. Of course, everybody probably knows there's 2 types of something called charge, which at the time were named plus and minus. Okay, we don't really know which one's plus and which one's minus, except by definition. we've all probably learned in high school that unlike charges attract and like charges repel. So the force is somewhat easy to understand in that sense. And if you get a little bit further on, we have the idea that the force is transmitted by fields, that there's an electric field in space, and it's sitting out there, and it has its own sort of entity. It's not just a mathematical tool necessarily, but it actually has energy in it, which can be transmitted because that's what light is. It's moving electromagnetic field energy. All right. One of the things that is typical of this force is that it gets weaker as the charges are pulled apart. Their interaction together gets weaker and weaker and weaker. So let's now contrast that with color forces. So now we have three types of something. And since there was an idea that you wanted to be able to create something neutral, people chose the idea of colors because there's this observation that if you take red, green, and blue light and combine them, you get something that's white. In fact, they named them that. Of course, the quarks themselves are not red, green, or blue. It's just a name we have made up, maybe whimsical, but it's probably more fun than A, B, and C type. But essentially, that we have those three types. And now it turns out that it gets pretty complicated. You can't make a simple rule that says like and unlike colors attract or repel. They can both attract and repel, depending on their motion and the state that they're in. We do go back to the idea that the force is transmitted by color fields. There's a field of energy in between them. And the other amazing thing is that if you try to pull them apart, this force stays strong. It doesn't get weaker as they're pulled apart. I just wanted to show you a little bit of graphs about that. Hopefully this is not too technical. This is a potential energy for for an electric particle in a field. And this is what I mean by it gets weaker. It's very hard. The slope of this is the force. This is the energy. The energy increases and then it just kind of levels off. And if I think of the force is very strong here, and then it levels off, which means the force is getting weaker there. On the other hand, if I make up a kind of effective potential for quarks, then it also has this steep part at the beginning, but then instead of rolling off and sort of going to zero, it just keeps increasing, which means the force just keeps staying there. It's not getting bigger, but it is just not diminishing at all right? The other thing that's quite different is EM fields have no charge. There's nothing there that's charged. They act between charges. Color fields actually carry charge, and that means they can interact with themselves, just in the same way the colored quarks can. The gluons can interact with themselves as well. They don't need an intermediary quark in order to do that. So this is the thing that also rather whimsically gave this kind of colored quark field or color field the name glue, because glue sort of sticks to itself. And I'll give you a better reason for why people call that. But this is where the name for the gluonic field came from. It's basically this kind of self-interaction makes the field sort of interact with itself and stick to itself. So here's just an example. Here's an electric field lines. These are the force lines that come from just a positive and minus charge. And you can see they're spreading out in space and they move around. This is what's called a classic dipole field that's strong in places and weak in places. But when you look at gluon fields, because they stick together, they form a tube, which is generically sort of called a flux tube that goes between the two quarks. And because they're all attracted to each other, they form this little tube. And it's in some sense very similar to like a rubber band, where the force is just directed along a line. If I rope this around, and hopefully don't rip the thing out of the floor, right? The force is just coming straight through here. Now, if I pull harder on this one, the force definitely gets stronger. That's not what 2CD is doing, right? It's just somehow staying the same. So springs, actually, the force just gets stronger and stronger and stronger as you go. But we'll talk about what happens when you get too strong in just a minute. But it's very similar type of force, whereas the electromagnetic is spread out all over the place, and it's quite different. So that's the kind of gluey aspect of this. So let's just also talk about, at the fundamental quark level, what people call these things. If you do the quantum mechanics of the electromagnetic force, there is a force carrier called the photon. discovered through the photoelectric effect, revolutionized created quantum mechanics almost. It was that this field actually came in little packets. And it's massless, and it doesn't have any charge, but of course it has energy in it, in the field energy. And there's a famous formula for what that energy of a photon actually is. Quantum color force is carried by what we call these gluons. They're also massless, they also have energy, but amazingly they carry both a color and an anticolor at the same time. So this is really sort of weird. We have both colors and anticolors. So I really should have said we had 6 colors, not just 3, because we have the anticolors as well, right? So those combinations lead to a whole bunch of different types of gluons. There's the red anti-red, there's the red anti-green, the red anti-blue, and then the next cycle of green anti-red, green anti-green, green anti-blue, and then all the blue cycle. And if you just counted all those up, you'd think we have 9 types of gluons, sorry. It turns out it's a little bit more complicated than that, and the number reduces to 8 instead of 9. Why is that? Well, it's related to something called color confinement. So let's discuss what color confinement actually is. Basically, it says that we have never observed bare color outside of a space of around a femtometer. We just don't see states that have color outside that. And that means because we don't see color outside that, the particles don't have any long-range interaction. If I have a colorless object over here and a colorless object over there, and they're not within a femtometer of each other, they don't see each other. They don't have any interaction. So what happens with the rubber band as I pull it? I pull it harder and harder and harder, and if it's secured to the wall, I know what'll happen if this one I'll probably rip the thing out of the ground. But let's just say, it's even more dynamic than that. Let's just say I had something strong and I pulled and pulled and pulled and pulled. What do you think would happen to the band eventually? It just breaks, right? It just breaks. That means the chemical bonds in here have broken between the atoms, all right? And so that's not a surprising expectation. So what happens when we have the flux tube? All right, we're pulling the quarks together. Maybe we hit one and it's flying off to the side. We're pulling it, and it just gets to be more and more and more energy in the string as it goes farther and further and further. And then it breaks. But when it breaks, it can't just have a bare flopping end of this flux tube, because that would leave this unattached color line. So what happens? What does it do? I could just create a quark there and say, okay, I pull a quark from somewhere. But quarks have electric charge. I'm not allowed to just make one. We'll say a little more on that. So what's the solution to this? It's antimatter, all right? So when you pull that string apart, you're going to create antimatter, which has been one of the things fascinating to science fiction. There's from Star Wars, you can see the antimatter dilithium crystals, which power the Enterprise. So surely if it's in TV, it must exist. So what is it? In 1928, Paul Dirac, a famous theorist, developed a theory that said electrons would have positively charged cousins called positrons. And they would look just like an electron, but they would be positively charged. And then they were discovered by Carl Anderson in 1932. So the basic rule is an antimatter fundamental particle has the same mass, but opposite electric charge from its matter cousin. So let's just go through what some of these particles are. There's the electron has its cousin, the positron. The muon has the antimuon. The tau has the anti-tau. And then all the neutrinos have antineutrino types. There's another whole story in the fact that it's not as symmetric as you might think there, but it has to do with the spin states. Then you have the up and the anti-up, the down, the anti-down, strange, anti-strange, charm and anti-charm, and bottom and all the rest of them. Right? So that's a kind of a nice pattern. Everything that there's a matter version, there's an antimatter version of it. It turns out you can make anti-atoms too. In Switzerland, in CERN, They made a bunch of antiprotons and they made some anti-electrons and they actually got them together and formed antihydrogen. Using an accelerator or anything, this was pretty expensive, so if you made a gram of antihydrogen, it would cost quite a bit of money these days, $96 trillion. Of course, they didn't make a gram of it, so which would be like Avogadro's number of them. But it has been achieved. You can make these antimatter atoms and things. And antimatter is actually routinely created. How do we do it? In high-energy collisions with either from nature or in man-made particle accelerators, if you have a very energetic collision, you can turn some of that collision energy into matter. Remember the famous equal mc squared. And it always appears as matter-antimatter particles, pairs of particles, and they have to be these mirror pairs of plus and minus. So for instance, it has to be up and anti-up, or it has to be muon, anti-muon. It can't be up and anti-muon, or up and anti-charm, or something like that. They have to go together. So you can't just create one or the other. You got to create both of them at the same time if you're going to create them. And also, one of the things people wonder is, well, what happens when matter meets antimatter? The particles annihilate. They just disappear, and energy comes out of them. This is a quite common occurrence that occurs in nature all the time. But there are some rules to this game. One is that when you create or annihilate a matter-antimatter pair, they have to be the same type. And charge has to be conserved. So for instance, I couldn't have done an up and an anti-electron because then I would have 2/3 on one side and -1 on the other, and I'd be left over with that. But it's even stronger than that. They have to be both up and an anti-up, an electron and a positron. But you cannot just mix particles, mix antimatter together and have it all just dissociate. So for instance, that antihydrogen only annihilates when it hits either a proton or a real electron. It doesn't annihilate itself. The anti-electron and the antiproton do not themselves annihilate. Okay? These are kind of examples of conservation laws that we have in particle physics. Some of the ones for fundamental particles that you may have heard of is that, as I've sort of said before, electric charge must be conserved. This is probably one of the strongest laws we know. We've never observed a failure of it, and people have looked. People have tried to find places where electric charge was not conserved. But as far as we can tell, there's never a net change. You can change the amount of plus, but you've got to change the amount of minus at just the same time. Another one, just since we talked about leptons, is it turns out lepton type number has to be conserved. So if you start out with a certain number of counted electrons, somehow they have to stay the same. That you can't get rid of them. They can't just disappear. Another one which is not so strong is called the quark flavor. That's the flavor is the up and down and strange and charm. Those, it turns out, they can change. The glue force does not change them, but there turns out to be a weak force which can actually change those flavors. But typically they're not unless that weak interaction is involved. So let's go back to this idea of color confinement and breaking in the flux tube. Here I have two quarks. They're being pulled apart. Here's the flux tube. And then when I get enough energy that's in this field, suddenly I create a quark-antiquark pair, and now two particles move off in presumably opposite directions, and I've managed to make sure that I can have something which is a color neutral object, the color confinement, but I've taken energy out of the string so that these particles can move apart. So that's the basic structure of a string break. This can happen multiple times as the string. They still have made lots of energy in the field, and it may create more and more of these particles. So color's confined because of this being able to pull these quarks and antiquarks out of the vacuum. You can always manage to hide the color, so you never, ever see it in the outside world. It's always hidden inside of the particle with the colored quarks and the gluons. And that's because when you pull them more than a femtometer apart, the energy is sufficient to create the quark-antiquark pair. And that's why that's the scale, because just the energy drives it to say, it's better for me to make a quark-antiquark pair than it is to have this long stretched string. And that result is we never see long-range color forces. All right? But that explains the mystery of how I got from 9 to 8. If we used a combination gluon that was red anti-red, green anti-green, and blue anti-blue, that's colorless. So that ought to be able to just fly out to infinity. I ought to be able to get long-range forces that come from this object, this gluonic object, right? Because it's already color singlet. But it turns out we don't ever see that. And if the theory has it built in that we will never see that, that would violate the symmetry of the theory between all these colors. So that gets rid of that one extra one that we talked about before. All right. Just so you know it, the theory that describes all these colored charges and fields has a fancy name. It's called quantum chromodynamics, which almost nobody says too many times in a row, so we use the slang QCD to discuss it, where we're really sort of, the QCD is a label that can be used on almost anything, and it just basically means you're talking about something governed by color forces and the color fields, the gluonic fields that we have. This turns out to be a very mathematically complex theory. It's not simple, and that means that solutions for solving bound states and things like that are really very difficult to calculate unless you use very large computers, which are only in the last 5 years getting powerful enough to calculate what is happening with quarks interacting with a gluon field. And just to say it, part of the difficulty of this calculation is that I don't just get to stick with the quarks that I have and their interaction with the gluon. This fact that when they move far apart, that they can create extra particles that might virtually be created and interact with it means I don't even have a fixed number of particles in my problem. I can't just sit down and say proton here, electron here, or maybe 2 electrons. I know how many particles I have. I might have 3 particles, I might have 5, I might have 2. There's all these different possibilities that nature has in this bound state. So calculating them all on a space-time grid, which is small enough and to get the accuracy, has proved a real challenge for many. And we actually have a quite active group here in the physics department that have done some major calculations of these. So let me show you some of this. This is a simulation showing a quark-antiquark pair moving apart in time, and you can see that there's this flux tube that's being pulled apart. This is a little bit fake in the sense that for a quark-antiquark pair, they ought to be anti-colors, but there's no way to draw anti-red, so they just made it blue. And the other thing that's funny is that since the gluon field itself is carrying color, those colors are rapidly changing all the time. They're not just staying constant. The red one doesn't just stay red all the time. It's flickering back and forth to all kinds of different colors as it goes. That's the quark-antiquark pair, which makes up a lot of different types of particle in nature. Here is the proton. And of course, all of these are slowed way down so we can see them. In real life, they're all happening at 10 to the minus 20 seconds between each step, impossibly fast for us to even think about it. And so here you sort of see 3 quarks in a particular mode where they're stretching apart. And you can see the gluon fields forming this kind of odd shape where it forms this kind of flux tube. It doesn't want to just spread out all over the place. It wants to form this kind of a tube as these things move. Again, the colors here would never actually be constant. They would be constantly changing because of the way the glue field can carry color and anti-color and change all the colors of the quarks. All right. This is a simulation which is actually just about the gluon energy. And I like this one because it's a little bit more realistic in the sense you see that these fields are just rapidly changing all over the place. The colors are, in fact, just trying to get some idea of how the color moves around. But of course, carrying color and anti-color, we can't really easily plot such a thing. But here on this grid, this was calculated, you can see how dynamic it is and how challenging for a computer this would be to try to calculate something changing so rapidly and changing all over in space. It's not just something that's simply bubbling there. It's quite dynamic in its shape and in its motion. All right. So another thing I'd like to bring up is the mystery of the mass of the proton. You may not have thought it was mysterious, but the proton has a mass of, in these funny units, 2 times 10 to the minus 27 kilogram. And it's made up of 2 up quarks and a down quark. That'll give you the single plus E that we know has to be. But if you look at what the mass of up and down quarks are, they're a very, very small fraction of what that total mass is. It's 0.005, all right, so 3 of them is 0.015 relative to 2. That's an enormous amount of energy that is not coming from the masses of the thing that make up the proton. So what does that tell us? Well, we only have 2 choices. The rest is either pure kinetic energy of the things flying around inside there, or it's the energy that's in the gluonic force field itself. It has energy, and it's not a little bit. If you look at a hydrogen atom, it actually is a little bit different in its mass from a proton and electron because it's bound. But it's 1 part, I think, in about 1,000,000 that it changes its mass because of that. Here, it's just the other extreme. You've got 3 little light things, and the mass is just enormous relative to that. So we've discovered from experiments that this force field is about half the mass of the proton. That means you are about half gluonic mass because you're made of protons. Neutrons are the same. So we're all sitting here just filled with gluonic energy. You bet you never even thought about it. Let me just try to walk you through a picture here of what the actual distributions look like. I apologize for this plot. Basically, I'm looking at the quark or gluon momentum here and the amount of it that's in a nucleus. It's on this weird log plot because that's how everybody likes to plot it. But I want to just point out some major features here. Here's the up and down quarks that we were talking about. And notice the up is about twice the down, just the way we talked about. And this is at the sort of a momentum, which is what you'd roughly expect, about 1/3 of the momentum of the proton. But notice this red line. They had to divide it by 10. The gluons are just enormous. There's an enormous amount of glue energy going on here. You'll see these other things here, CC bar, SS bar, U bar, and D bar. So it turns out that the nucleon also has significant amounts of antiquarks in it. They're virtual. They're not there all the time. But if I get down to really, really, really short times, every once in a while, one of those gluons will split into a quark-antiquark pair. Heisenberg uncertainty principle says it can't last because it's violating energy conservation, so then it just disappears. So I only see that if I look at extremely, extremely short times. And that's what this high resolution is. I've gone to extremely short times, and notice how many more of these antiquarks that I see, as well as gluons. So this is actually a real sort of a funny thing. When you study the structure of the proton, you're averaging over so much bubbling activity that you have to be very careful about defining what time resolution am I looking at so that I know whether to expect all these little fluctuations to have averaged out or whether they're still going to be there. So I did want to say a few words on how we study gluons and quarks experimentally. To go to very small distances, we need high-energy particle accelerators. It's just a basic fact of the way the wavelength of your probe changes with energy, that very, very high energy means very, very, very short distances and very, very short times. So that's why we build these high-energy particle accelerators. Here's one that's in Brookhaven out on Long Island. It's called RIC. You can see it's a picture from up in the sky from an airplane. So this is a rather enormous thing. It has both protons which collide in it, as well as heavier nuclei, very heavy nuclei, some of them which can be brought into collision at particular experimental areas. This is an accelerator I work at. Sorry, I didn't realize it was going to be so blurry. This is in Virginia. It's called Jefferson Lab. It uses a very intense electron beam, and the electron beam scatters actually off of the quarks inside. And all of these, of course, being accelerators, and this is from the LHC and CERN, have these long, long pipes in them where the protons or the electrons travel as they are accelerated up to these very, very high energies. And this one in particular, you have to remember, this is a thing which is like 27 kilometers around or something. So that's a long, long tunnel. All right. The two basic ways we go after glue, one is that we scatter protons and nuclei from each other. They're full of glue, so if we scatter them, some of the time what's going to happen is the glue is going to interact. So here's what's called a Feynman diagram, although it's really a cartoon in this case. Here's a proton coming in. You can see little arrows. Here's three little different quarks and a gluon. And then here's another proton coming in from this side. And they get very close and they interact. And then I get some kind of interaction. The quark from this one interacted with the gluon from that one. It creates some kind of excited state here, which they call the Q star. And then off comes other particles from that. So that's the way we can probe the glue, as we scatter protons off of each other and nuclei off of each other. Another way to try to study gluons is not very apparent. We do what we do in Virginia, which is we have an electron beam coming in, scattering. When it scatters, it exchanges that quantum of light, the photon here, and that interacts with one of the quarks and gives it a big kick. Now, gluon doesn't have electric charge, so it cannot interact directly with the gluon. So electrons, at first sight, would not seem to be a very useful tool for that. But it turns out that we can use them because this radiation of gluons you can see there affects what happens. So we can actually study, as we change the photon energy, we can study how these gluon radiation changes. But then another enormous part of it is we've struck a quark. We are pulling it out of the nucleon now, and it's going to turn into hadrons. And so these charged particles made up of quarks. So we can actually study how that process happens. We give it a known kick, and then we look at the particles that come out the other side, and we can study their composition, what kind of quarks they have in them, and not only learn about what we hit, but also learn about the process that turns into a hadron, which is what these things like pions and protons and stuff are. Right? So let me finish up here. The visible matter in the universe gets a lot of its mass from the gluon field. That's the main thing. But we still have a lot of mysteries. There's still a lot of work going on. We still don't really understand how the quarks and glue form a stable state, and we don't really know much about its structure at this point. For instance, do the quarks orbit around inside there, or do they only go back and forth? They actually have little spins. How are the spins lined up? There's a lot we don't know yet about just how the proton structure or the neutron structure is made up, or even some of these other hadrons, which are simple. There's actually an active program to also see if we could make just purely gluonic matter. They're called glue balls. They haven't been actually discovered yet, but it turns out that the QCD theory allows you to make a little object which is color neutral, but it's actually only made of glue. There's no quarks in it at all. So there's a lot of people looking for that. And then there's a final question I would say is that, can we do anything to kind of get around nature and deconfine the color? And here I would say yes. We have succeeded in deconfining the quarks and glue for a very brief time and in a very large region, but we've used these heavy ion collisions I mentioned earlier at Brookhaven to create a hot plasma of free quarks and gluons. And I don't know if you've seen this picture, but it's just this absolutely stunning picture of a collision with all of these particles streaming out from this collision area. And just to be clear, while the plasma is formed, they are deconfined in the sense that they're all not connected with little flux tubes. But in fact, as they spread out, nature steps right back in and makes them colorless particles. So by the time they get to our detectors, they're all nicely colorless particles, as they should be. All right? So I just want to close with saying, quark and gluon dynamics is really very different from any other physical system. These very high energies, very small spaces, strange color forces, there really is just nothing like it. And these are very, very strong forces. And to boot, the quarks are moving very, very fast. So it's not something nice. It's not like a planet nicely orbiting that I can follow. it's actually quite difficult even sometimes to think about with these motions being so relativistic. But then to pull it all together, understanding the proton means you can explain the mass that we see everywhere around us that is what's called the visible mass. No idea about dark matter yet, but in terms of the stars and the galaxies and everything we see, if we can understand the proton mass, then we understand that mass as well. All right, so let me thank you for that. And if there's any questions, I'm happy to take them. Here's one, Paul. Thank you. Oh.
I had a question about this quality of color and the emergence of it. I read that it was because quarks in protons were violating conservation of angular momentum due to Fermi statistics. I never really understood that, so I was wondering if you could elaborate.
Oh, so you're talking about a really nice historical puzzle. So you probably know that when you have identical particles and they're fermions, they have spin 1/2, they can't all be in the same state. And so at some point, when they were making this model, they originally just made it with quarks. They didn't have a good theory about the interaction among them. They didn't have color. They didn't have any of that business. And they discovered that they had a particle that was 3 up quarks in the same state. Oops. So that wasn't allowed. So then the invention that did that was to give them a color degree of freedom, because there's now 3 different colors, so they can all be in the same state in terms of where they are in space and all that kind of stuff, even spin, but with different colors, they're not identical anymore. They're different. They have a different aspect to them. And that was the solution. That was where the whole quantum chromatics came out of, solving that problem when they realized that their regular quark model would not explain this. The other possibility was to throw out the Fermi-Dirac principle. They weren't ready to do that.
With regards to the flux tubes, is there a certain distance where they will break and create the?
It's about a Fermi, about this femtometer.
Okay. And is that dependent on the color between the two, or is it about the same?
Well, the flux tube is actually a mixture of many different gluons all attracted to each other. So it itself doesn't have a single color label to it. It's a mixture of both. But the interactions between them are such that when it gets beyond around a femtometer, the energy in the field, it's not that the field doesn't care, the field can go up to whatever it wants to, but it's enough energy that you'll get this fluctuation that says, oh, wait a minute, I can make a quark-antiquark pair and lower my energy. And so it does it. When it does it, it's totally random and statistical. You can't predict when the string is going to break. Yep.
I know you showed us an example of 3 quarks with like the flux tube that goes like this. I was wondering what the colors would look like, because when you talked about colors with like 1-on-1, you said one was one color and one was an anti-color.
Right. So let me back up and see if I can get to that. No, it's not going to let me. Maybe it will. Yeah, get back to that simulation. So whenever they make these simulations, they're simplifying the situation. So the flux tube itself, as I was saying, is a mixture of many gluons. So it doesn't have one color to it. And in fact, it has anticolors. Now, if you're really into optics and color theory, there are actually such things as anticolors, right? There's the two that somehow cyan is the opposite of something or other, and it's different whether it's light or paint, and there's a whole bunch of stuff I don't know about. Here, what they wanted to do was they didn't want to have to show that these were changing color and to anticolor all the time. Actually, these are quarks, so they stay colored all the time. They're either red, blue, or green, but they wouldn't just stay one color. The flux tube would have color flowing in and out of it in a way that they would fluctuate to red, to green, to blue, to red, to green, to blue, to red, to green, to blue. So that the net whole thing together stays color neutral. And that's part of what we don't understand, right? Somehow or other, nature knows how to take all of that mess and keep it color neutral. And part of the theory suggests that the reason is that it can't do it if it gets bigger than around a Fermi. So that's somehow the limit of what you can do to keep the whole thing color neutral. After that, it's color unneutral and immediately starts sucking particles out of the vacuum and makes itself neutral again.
Thank you.
So I've heard of this idea of like particles being colorless versus color neutral. So you said that when there's a whole mess, it ends up becoming color neutral, right? It can't be colorless then?
If they're quarks, no. Quarks or gluons, no. They always have some color. That's part of their intrinsic nature. For the reason you mentioned, right? If they didn't have it and I had colorless quarks, then I could put them in a state and violate the Fermi principle. Now, there are lots of other particles that don't, electrons don't have color. None of the leptons have color. Neutrinos don't have color. So there are lots of particles in nature that don't have color. But if it's made up of quarks, or if they find the elusive glue ball, those will be colorless, but they will be made of colored objects. There was a question over here, actually. Well,
Nice. So in QED, you can like represent everything with SU2, which double covers SO3. Although for QCD, everything is in SU like 3. So what are the actual physical interpretations of the SU3 and like the group generators and the structure that comes from that?
well, I'm not sure what the best answer to that is. I'm not a theorist, number one, so I'll predicate that with that. However, what you're talking about is that the operators in the photon, they have a gauge coupling which just goes to the charge. And that gauge coupling, instead of just being a charge, now is a 3-columned matrix. And the gluons are now represented by matrices, 3x3 matrices, that have all that color, anti-color into it. Well, I didn't want to go into the math of it, but it turns out when you fully develop the theory, you don't just have red, anti-red, green, anti-green. You do mixtures of them, and that satisfies the gauge properties of the theory so that everything works nicely out in it. And you just have these matrices. So instead of a simple product of potential and charge, I now get this matrix that's hidden up in the not commutator, but the propagator, and it just makes extra math. But the real problem is in electromagnetism, if you look in the Lagrangian, there is no photon-photon part, right? And the QCD has a gluon-gluon, there's a gluon field thing. That's that self-interaction, and that turns out to be really, really hard to deal with.
You had one slide showing matter and antimatter that didn't seem to have any reason to annihilate each other. So what is the nature of when they're the same?
For instance, if you have an electron and an anti-electron, they're oppositely charged, so they'll attract. So they will pull themselves together until they get close enough for their fields to interact, and then they will, with some probability, annihilate. The anti-quarks, same way, they feel this color force. They also have they're charged too, so they also have a charge force, both charge and color, pulling them potentially together. And so that's usually the annihilation force that comes from the fact they're oppositely charged or oppositely colored.
So their lifespan is extremely short.
It just depends. Usually, the process that takes a long time is for them to get close enough to annihilate. So if you make an anti-electron, like in the room here, which is actually probably being done by cosmic rays as we sit here, it's going to wander around, it's going to find an atom, and then eventually it'll work its way and get close to an electron in an atom, which there's abundant around it, and then it will annihilate in that moment very, 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 very fast. It's not a slow process. This poor guy has been waiting forever.
So there was one part where you're talking about how the gluon, there's like 9 different ways it can be, but actually it's 8 because you can't have red anti-red plus green anti-green plus blue anti-blue. So what are those remaining 8?
Oh, so they're just different combinations of them. So there's one that has red anti-red, green anti-green, blue anti-blue, but they're not all equal. And that one is sitting there. And then there's one that's like red anti-red minus green anti-green, and one that's red anti-red plus green anti-green. They're just different combinations of them. And it's just to make the math easier, frankly. No one's ever, it's these matrices that we were just talking about. The math of them, if you put them in a nice mathematical form, says these are the combinations which make the math the simplest. As in always these things, you can almost always develop any representation and mixture that you want, but it may make the math harder or simpler depending on how you do it.
Thank you.
So was that put in initially by hand, or was it somehow part of the general structure of
You're diagonalizing
chromodynamics?
these matrices. When you diagonalize these matrices, you do it in a way that changes. If you just start with the colors by color, and that matrix between them has these terms, and you try to make it diagonal,
Right.
then you choose different combinations, which makes
So it naturally comes out of.
Yeah, it's not. Yeah, it's
Okay,
not. It's not. If you were doing it, if you were taking graduate quantum, you could do it. It's not. It's not something that requires.
Haven't taken that in a while.
PhD to do. Well, it's one of those things. QCD is not something that you would get in in your first year graduate school, because in your first graduate school, they're just trying to teach you really good, strong, regular things. If you take quantum field theory and then you take the second semester, then they'll finally say, okay, we did QED, now it's time to attack QCD.
It's traceless or something.
Yeah, exactly.
And that's what makes it work. Okay.
All these technical math theory terms.
I've only looked into this a little, so I'm not fully sure if like what I'm gonna say is correct. But I was curious, like that kind of giant 3x3 block of all of like the gluon interactions with the different colors. Does that like plot come from the path integrals, like from evaluating the Feynman diagrams for that sort of thing, or would that be something else?
Or this was something in my talk?
I think like the block, that one.
That one?
Yes.
So that is a numerical calculation. So they set up a lattice of points, and they have somewhere they have some charges, which are color charges, and then they calculate the fields that would interact between these, and at every little point in space, it has to satisfy certain requirements, basically something called gauge invariance, and each little bit interacts with each little bit and each little bit in that. You can do the same thing with electromagnetism. You can make an electric field by making a big grid, putting some charges on it, and then just calculate the field from each point and then connect them all up. Actually, I think you can find, there's some fields you can find using Excel. You just set up your grid in Excel and let it go. That would not work for QCD, but for electromagnetism, where the math is much simpler, you're just setting up a grid and solving boundary problems, basically.
Okay.
And that's what this is. But you can see it's quite dynamic. It doesn't just fall into some state and then just freezes there. Oops.
I had a question on the slide where you had the proton collisions, and I was just kind of curious if you could go into a little bit more detail on that. I think it was Q star collides into Q.
So this is this is a particular reaction. So when you take a proton, which is a relatively complex thing, which got gluons and up and down quarks, I showed you an antiquarks and things like that. When they collide at high energy, any number of these things might collide. So I might have a quark-quark interaction. I might have a gluon from here that interacted with a quark up there. You can even sometimes have collisions where two quarks happen to interact with each other. But it's actually, since they're tiny, they have point-like interactions to get close. When you actually do this, you have to sum up over many, many different mechanisms, not just this one. This is not the only one that happens. By Q star, I think what this person was saying is simply, I had a quark here. It absorbed some energy, momentum, and color, frankly. And actually, at this point, it's violating energy momentum conservation. This is true even in classical physics. You can't have two things come together and then just stick together and go off to infinity that way. You can't satisfy energy momentum conservation. They have to break apart into two again, somehow. So I think in this case, he just uses this Q star not as a new particle, but as some quark, which has somehow got more energy and momentum than it should relative to its mass and its speed. And they have a generic name of being off shell, but actually for fundamental particles, it's not clear things can really be off shell. They just have an energy momentum relationship, which is not exactly right. And that's well known from Heisenberg uncertainty principle that can happen.
And is that something that can be measured like at the particle colliders, like with the sensors, or is that just more of a theoretical?
No, they would not be able to see at this time scale. This is happening very deep inside the collision, and by the time everything gets out very far, they could tell that this particular reaction might be going, because some of the times what happens is that I might have a very high energetic gamma here hitting a very low energy U, and that will cause the momentum in the detector to go in the direction of the gluon. So these funny little things don't give you the full sense of things colliding and like billiard balls, pieces of them flying off of each other. And you can actually infer something about what the momenta of these different things were by looking at where these things go in your detector.
Thanks.
So as he said before, there's not you can't combine the green and anti-green and red and anti-red, so on. But you can combine just red and green.
No.
Oh, you
The
can't.
gluon has to have a color and an any-color.
Okay.
And the reason is that if I have a blue quark here that I'm going to change to green, I have to come in with green anti-blue. The anti-blue cancels the blue on the quark, and then the green is left over on the quark. All right, so that the quark anti-quark thing is what allows this mechanism of changing the color of the quark.
Hi, could you speak a little bit about what kind of experiments exactly led to knowing like all that extra mass that's inside, you said the gluonic field?
So one of the things that was, part of this was known by sort of in the dark matter sense. When they first started scattering electrons off of quarks, which is how quarks were experimentally discovered, was scattering off of little point objects inside of a proton, which was not a point object. They could tell when they scattered and they looked at the products what the momentum of the quark was initially. So they scattered over lots of different angles and stuff, and they measured that momentum. They summed it up, and it was half of what the value should be if it was going to be the full mass of the proton. So that was the first hint that, half of the energy of the proton is not in the quarks, and the only other thing in there is the glue. So that was the first hint that the glue was the major part. Then when you get to these proton scatterings, now you're scattering a glue object with a glue object, and there it's more complicated analysis, but in fact you can also just, you can kind of find glue-glue interactions, so you can actually do the same sort of game of scattering a gluon off of a gluon, and then you add up how much you have, and you find out that you can determine the distribution in momentum of the gluons inside of the nucleon. But it's a significantly harder analysis because you have two complicated objects interacting with each other. The virtue of the electron one is that the electron side doesn't know anything about color. So it just comes in and gives a quark a knock, and then you look at what happens after that.
And you said that they could gluon and gluon collisions. They could do. How do they isolate gluons and do that?
So when you have gluons and gluons, there's no quark line, right? There's a glue here and glue here and glue here and glue here comes out. So gluons, when they make a set of particles, will not have a net charge to them because the gluon doesn't have a net charge. But if you have this quark scattering, somewhere there's some charge that came from that quark. So if you look at the net charge of this thing of particles coming out, if it has a net charge, it probably came from a quark. If it doesn't, it probably came from a gluon. In fact, that's one of the first observations of QCD, of real seeing the effect of gluons, was that they had these events where an electron scattered and they could see 2 electron tracks, and then there was this other track coming out that was neutral. And so they could figure out that, oh, it's a gluon.
Okay, so it's 3:30, so one last question.
Much like how there's 2 up quarks and a down quark and a proton, where do the strange and charm quarks and the other quarks reside in? Like, where can we find them?
So it turns out that what I was talking about earlier, but I didn't go into a lot due to time, is that the gluons are also inside the nucleon making these virtual pairs. So every now and then, this actually happens in the hydrogen atom too. You get little plus and minus, you may not know, but plus and minus electrons kind of buzz around outside of hydrogen atoms and things too. But you can there's so much energy in the glue field that, remember, a quark is only like 5 on this scale, and the gluon energy is 500. So there's plenty of energy in that gluon field to suddenly make a quark-any-quark pair. But again, for that reason, if it creates that quark-any-quark pair, that energy of the mass came from somewhere. It's violating energy momentum conservation. Suddenly, the proton got heavier. That can't last. Heisenberg uncertainty principle says it can only last a certain amount of time, and then they annihilate back into the sea. So that quark-any-quark generation from gluons, it doesn't care, other than the mass, it doesn't care what other kind of what the flavor of the particle is. So you get up and anti-up, down and anti-down, strange and anti-strange, charm and anti-charm. The really heavy ones, like top and bottom, are heavier than the proton, so they don't happen very often. In principle, they could, but they don't. So inside the regular proton, that's where you have these other quarks. However, there are other particles you can make that just have a strange quark in them that, you know, is sitting there in the particle, and it just stays there in the particle, and might be a strange and an anti-up. There's I don't know if you've ever seen it, there was what's called the zoo of particles, where there's just a zillion different types of particles. Some of them have strange quarks in them, some of them have charm quarks in them. Some of them have bottom quarks in them, you know. So of these hundreds and hundreds of particles, most of them, of the heavier ones, often have one of these heavier quarks in them. And you have to make them, right? They will decay eventually. So they have to be made with a high energy accelerator or with the cosmic rays that come out of space or something like that. An interesting idea is that the energy inside of a neutron star, which is very dense matter, might actually be able to support strange quarks inside there. So that's an active area of research, of looking if neutron stars might actually have stable, strange particles in them. Glue.